Welcome to screencast of 5.8, the rational zero theorem. So one thing I want to mention is that the word zero, solution, root, x-intercept all mean the exact same thing. So the rational zero theorem says if we're given a polynomial function and none of its roots, instead of just plugging in random numbers until we find a zero, till we find a root, what we can do is a zero rational theorem, because that's going to reveal all the possible rational roots. So then we could plug in those. Okay, so if I'm looking at a polynomial, like how you find all the zeros is you take all of your factors of the first leading coefficient. Just take all of those factors. The leading coefficient, this is going to be called Q. Then we take all of the factors of our constant term. So here this negative 40 is my P, and then we take each factor of 40 and divide it by all the factors of 6. So what this looks like is, let's see, P's factors, well, to get negative 40, I could have plus 1 times negative 40, or I could have minus 1 times positive 40, so plus 1 minus 1. I also have plus or minus 2, plus or minus 4. Let's see, maybe it'd be easier if we wrote out a chart of all the different factors. So 1 and 40, 2 and 20, 3 doesn't go in, 4 and 10, 5 and 8, 6 doesn't go in, 7 doesn't go in, and that's it. So I can list out all of my factors of 40. And so I could have positive 1, negative 40, or negative 1, positive 40. So that's why I'm having all of them be plus or minus. So plus or minus 1, 2, 4, let's see, 5, 8, 10, 20, and 40. Oops, plus or minus 40. Okay, so those are my factors of P. All right, my Q here was 6. So I need all the factors of 6. That's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are all the different factors that we could combine to multiply to 6. So I'm going to take every single term, every single factor of the 40 and divide by all the factors of Q. So the first one, if I divide everything by 1, I'll just get all the numbers that I originally had. So I can list it up here because I'm running out of room. P over Q will be, let's see, plus or minus 1, 2, 4, 5, oh my gosh, 8, 10, 20, 40. Okay, now I'm going to go through and I'm going to list out all the ones that divide by 2. So that includes, next line, this will be all of them. So this includes plus or minus a half. Oops. Includes plus or minus a half. I could do, let's see, plus or minus 2 divided by plus or minus 2. Well, that's the same thing as 1. I already have 1 listed up here, so I don't have to list it again. Okay, if I do plus or minus 4 divided by plus or minus 2, okay, that's the same thing as 2. I already have that listed here. Plus or minus 5 over 2. Plus or minus, let's see, plus or minus 8 over 2, because I'm just going through the list. Plus or minus 8 over 2 is the same thing as plus or minus 4. I already have that. Plus or minus 10 over 2 is the same thing as plus or minus 5. Plus or minus 20 over 2 is the same thing as 10. Plus or minus 40 over 2 is the same thing as plus or minus 20. Okay, so I don't want to write any repeated. Let's see, what else do I have? Now I have to go through and divide them all by 3. So plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 4 over 3, plus or minus 5 over 3, because none of these are repeated yet. Plus or minus 8 over 3, plus or minus 10 over 3, plus or minus 20 over 3, and plus or minus 40 over 3. Okay, so I have those done. Lastly, I want to include, I have to divide by every single factor. Oh my gosh, so this is a lot. So lastly, I'm going to divide them all by 6. So that's going to include Oh my gosh, let me just make this box. Okay, so plus or minus 1 over 6. If I do, let's see, plus or minus 2 over plus or minus 6, I have plus or minus a third. I already have that right here. Plus or minus 4 over 6 is the same thing as 2/3. I already have that. Plus or minus, okay, 5/6. Didn't have that yet. Plus or minus 8/3 is the same thing as 4 over 3. So I have that right here. Plus or minus 10/6 is the same thing as 5 over 3. So I already have that right there. 5/3 is already written out. Okay, how about 20 over 6 is the same thing as 10 over 3. So I have that right there. And plus or minus 40 over 3, because I divide, you know, the top by 2, the bottom by 2. I already have 20 over 3. Okay, so that's it. Those are all of my roots. They all have to be distinct, because I don't want any repeating. So that's what all the arrows are for. They're showing you all different ones. So knowing this, we can try out these next two. This example is going to list out all the possible rational roots of a polynomial function we do not want to solve. So go ahead, pause the video now, see if you can identify P and Q. List all the factors. So this one's a little easier. So Q is going to be the coefficient of my highest degree term. Well, since there's nothing written there, we can assume the coefficient was 1. The only factors of 1 are plus or minus 1. And then our P is going to be this 24, so all the factors of 24 are 1, 24, 2 and 12, 3 and 8, 4 and 6. So if you take all of these numbers and divide by 1, it's just going to be those numbers all over again. So P divided by Q, this gives you all the possible rational roots. We don't have to solve. This is it. This one's going to be a little harder, but go ahead, try to identify the P and Q, and then unpause the video and you can see what we do. So my Q is 3, my P is 10. If I list out all the factors of Q, the only things to multiply to 3 are 1 and 3. You can multiply 1 and 10 or 2 and 5 to get to 10. So if I take each of these terms and divide by the first term of factor of my Q, I get, well, let's see, 1 divided by 1 is 1, 1 divided by 2 is 2, 5 divided by 1 is 5, 10 divided by 1 is 10, and then I have to go through, and now I'm going to divide all of these by my 3. So plus or minus a third, plus or minus 2/3, plus or minus 5/3, and plus or minus 10/3. Notice we don't have any repeated, not like the first example. Awesome. So how do we actually find all our rational roots? So we're going to use a rational root theorem to identify all the possible rational zeros. What this means is we're going to test numbers using synthetic division and seeing which are 0. So if we don't have a remainder, that means it works. So if a number is 0 the function, then the remainder will be 0 when it's divided into the polynomial function. After we find one 0, we can use it to factor the polynomial and search for other zeros. So example 2 puts everything together. So it says use Descartes' rule of signs to identify the possible patterns of roots. Go ahead and try that. So I'm going to see how many positive roots I have. I have to see how many sign changes. So I'm going from positive to negative. So there's 1. Negative to negative, that's not a change. Negative to positive, that's a change. So I see I have 2 positive roots. The deal is you only can, you have to keep subtracting 2 until you reach 0 or 1. So if I subtract 2, I could also possibly have 0 positive roots. Now I want to find the negative roots. Okay, to find the negative roots, there's 2 ways you can think about it. Either you can plug in a value of negative x everywhere where you see x, alright, so negative x to the third power, so negative times a negative times a negative, well that's going to be negative. So negative x to the third. Let's see, negative times a negative is positive, so that guy, the negative x times negative x is just going to be positive x squared, so I keep the coefficient of negative 6. X squared, negative 13 times negative x, okay, so that's plus 13x, and then plus 42. So I see I only have one sign change when it's negative. The other way you could think about negative roots is you could just change the coefficient sign of all the odd exponents, meaning I could go through and just change the exponents. Change the coefficients that have an odd exponent. So these are odd exponents because technically this is 13x to the first. So this would give me negative x to the third minus 6x squared. Let's see, change the sign of negative 13, so it's plus 13x plus 42. I still get the same answer of one sign switch. So the possible pattern of roots, let's see, solve positive roots, negative roots, imaginary. How many roots should we have total? Let's see. If I have 2 shirts and 1 pair of pants, I'll have 2 combos. Since my highest exponent is 3 with the original function, I'm going to have 3 total roots. So if I have 2 positive roots and 1 negative, and I'm supposed to have 3 total, that leaves no room for any imaginary. If I have 0 roots plus 1 imaginary, and the total has to equal 3, 0 plus 1 is 1, plus what number equals 3? 2. So those are our only 2 combos. Alright, now we need to identify the possible rational zeros. Okay, so I need a P and a Q. So P values, Q values, and then P over Q. These are going to be my rational zeros. So my Q, well, the number that's in front of my x to the cube, it's just a 1. So my Q is a 1, so the factors are plus or minus 1, meaning whatever factors I find for my P are going to be my actual factors. Alright, so P is 42, so all the factors of 42, let's see what we get. 1 and 42, 2 and 21, 3 and 14, 4 doesn't go evenly, 5 doesn't go evenly, 6 and 7. Let's see, yeah, that's it. So I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 7, plus or minus 14, 21, and 42. So if I take each of these numbers and divide by 1, you get the exact same numbers. Okay, so my P divided by Q. 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 1 is 3, 6 divided by 1 is 6, 7 divided by 1 is 7, 14 divided by 1 is 14, 21 divided by 1 is 21, and 42. There we go. These are my possible rational zeros. Okay, so look up here, rational root theorem, check, I'm done. Step 2, I need to test numbers. Right, use synthetic division to find which, if any, are zeros of the function, so no remainder mean it works. So I just get to select one of these possible zeros. So before, we would have to just like guess and check and, you know, eventually stumble upon one. But here, we can actually guess. So I'm going to select positive 2. Let's see if 2 is actually a root. I'm going to use synthetic substitution, but synthetic substitution, well, just remember the remainder is going to be your answer. And if the remainder has to equal 0 if it's going to be a root. Let's see, so I have to go up to the original equation. Alright, let me erase all this. So I have to pick the coefficients. So in front of x cubed, I have 1, and then it's a negative 6 in front of x squared, negative 13 in front of x to the first, and then I have 42. Okay, hopefully this is going to be a factor. Bring down the 1, multiply by the 2, combine these, add them together, get negative 4, multiply by 2, get negative 8. Oh gosh, add them up, you get negative 21, multiply 2 and 21, negative 42. Oh, and you get 0 as a remainder. Awesome, so we did find a solution. If I found that the remainder was not equal to 0, guess what? I would have had to try synthetic all over again, because that meant I found something that's not the solution. Okay, so this corresponds to, well, since this used to be x to the third, I'm going to have one less exponent down here, so this is going to be x to the second, minus 4x minus 21. Okay, so that is, I found a root, right? The root I found was the x equals 2, And then I found this quadratic x squared minus 4x minus 21. So D is saying examine the depressed polynomial and find the remaining roots. So this is the depressed polynomial, meaning they just want us to take x squared minus 4x minus 21 and factor it. Okay, so what adds to -4 but multiplies to -21? Think about that for a second. So it's going to be -7 and 3, meaning our two factors are going to be x plus 3 and x minus 7. It wants us to find the remaining roots, so to find the root, I take x plus 3 equals 0 minus 3 on both sides. X equals -3, or x minus 7 equals 0, so you add 7 on both sides. X equals 7. These are the remaining roots. Perfect. And that's it. So we didn't do example 3, but the homework is 1 through 9. That's all. Make sure you ask if you have questions. Good luck.